problem similar to a Harvard MIT question. They have a competition, I guess, annually. But I want to work this simple example and show you how easy this problem is if you just have an idea where to start. I wouldn't know how to work it like so many of these things until I see the main idea. But I'm listing the multiples of 4 here. So 4 is certainly a multiple of itself. 8 is a multiple of 4. 12 is a multiple of 4. 16 is a multiple of 4. And finally, we get to 20. Now notice 20 is the only multiple of 5 in the list. All right, 20 is equal to 5 times 4. All right, so it's the very first multiple that is divisible by 5, right? And so for this example right here, the probability would be 1/5. Okay. Notice that 4 and 5 being relatively prime, 4 and 5 are what they call coprime, relatively prime. They don't share any common factors. Okay, and sometimes that's written like this, parenthetically, 4 comma 5 equals 1. Some people will write GCD out front for greatest common divisor. But notice that we could have just as easily picked 98, and you would just have a list. You would have 98, 196, and all the multiples all the way out, and the answer would still be 1/5, okay? So we're going to use that reasoning now, and again, I could go further with this. The next multiple would be 40, right? Where that was divisible by 5. What would be the next one here? 24. But you see, what we would get here, we would only get 2 over 10. Right? 2 over 10 of these multiples would be divisible by 5, namely 40 and 20, right? So this would go on ad infinitum in a periodic sort of way. All right. So anyway, the answer to this example is 4 out of 5, 1/5, excuse me. Now let's take a look at a problem with the numbers are slightly larger, and it's hard to do the mental math here. As you may have surmised, the prime factorizations come in very handy here. Notice what we're at. This is the prime factorization of 56. It's very easy to determine. 8 times 7 is 2 cubed times 7. All right, and that's 56. But notice what we're really asking here is 2/3 times 7 times m, okay? Let me put a dot right there, okay? So that's what we mean by a multiple of 56, and it's useful to leave this in its prime factorization, okay? Now, the divisor, okay, divisible by 686, that means we would place 2 times 7 cubed here, right? And so you see the only way for this to be divisible, for this to be an integer, is for m itself. Let me write this to the, m would have to be some multiple of 49. Okay, so I will call it 49k. See, isn't that kind of neat? And so in other words, unless that's supposed to be 49, not subscript, 49 times k. And hopefully that makes a lot of sense, because you would need a 7 squared up here to offset this 7 cubed, right? The k would just be some other integer, right? But you would need a 7 cubed here to offset this factor of 7 cubed, all right? And so what you would end up having is you would be interested in the number of multiples. Notice how 2 cubed over 2 is 4, and then 7 over 7 cubed. So this is equivalent to what we just said. Again, you would have 2 squared left times m over 7 squared, right? So you see, that's why we're looking for the probability of a multiple of 4 being divisible by 49. It's equivalent to this original question because of the way the prime factorization cancels out. Okay? And so in the very same sort of sense, divisible by 49, well, 49 and 4 are relatively prime. Let's write that down. And so the answer here is 1 over 49. In the very same sense that this is a very believable result because it's easy to write the numbers down. It's not quite as easy to write the numbers down here. But the answer to this question is 1 over 49. And of course, when we say selected randomly, that's the same as every outcome is equally likely. Okay, sometimes it's called a uniform distribution. Okay, but 1 over 49 is the solution. And just an idea of what it, if you don't believe this, the very next multiple, you would have to have 2 cubed times 7, and then m would have to be equal to 7 squared, right? Okay, like that. And then this would still be over 2 over 7 cubed, right? And you see, that means it's a multiple. That's equal to 4. Okay? And the very next time it would happen would be if you had 2 times 7 squared. Then the next time it would happen, it would be if you have 3 times 7 squared. Now, I won't write all that out. But notice this statement right here indicates the very first multiple. The multiples, m could be, maybe it'd help to do this, m equals 1. I'm sorry, let's write this k equals 1, okay? So it's more, let's see here. So we would have, I should write k equals 1, 2, 3, ellipsis, all the way up to 49, right? So you see the first 48 multiples would not evaluate to an integer. Okay, the first 48 multiples would not evaluate to an integer, but in this fashion right here, the 7 cubes cancel and you actually get 4, and this would be the very first multiple of that satisfied these conditions. But anyway, I hope that made sense, and I hope you can track it back to the fact that in this simple example, the answer is 1/5, and that's easy to see because the numbers are easier to write down. It's kind of tedious to write down all the numbers here, but the same thing is at work here. The very same idea is at work here. If you have a circumstance like this where the values are relatively prime, they're going to just repeat whatever the bigger number is. There's going to be a periodicity to when these multiples repeat. Okay, thank you for viewing.